Any questions? Anybody who wants clarification, explanation? Okay, so this is correct solution. Many of you got the right answers. I see that. Thank you. Now, did everybody get my email, which had sample exam problems in it, and list of suggested questions? You also know that Friday we have an exam during the class.
Is the exam 15 questions?
No, 5 questions. 1 question on each page. Totally you'll have 6 pages with the cover page. And some questions has A and B. But 5 questions and each question on each page. They're all 20 points. Total is 100. The coverage is end of the last lecture. So stirring numbers are covered. Inclusion, exclusion is in there. So you have to study the Friday material. Another thing I should say, we have 2 rooms here. So half of you will be coming to this room. So if your last name is before Karagüzer, you come here. Otherwise, you go to SAS 05, which is across and cross. Okay, it's all in the email. If you got the email, that's the information I have. 05. So we have 2 rooms, 05 and 03. So if your last name is in the smaller range, come to the smaller room, 03. Okay. Any other questions? On Thursday, I have office hour at 1:30 until 3:30. So if you have questions, you can come. But today we will do mostly problem solving for the exam. So I hope it will help you to understand what kind of exam questions you will. These questions I send you are very good examples of exam questions. So if you do nothing else, I will suggest that solve those questions at least. Okay, so one of the questions I have in the exam, which is a variation of this question, which maybe we can start with this. So it says, what are the integer solutions? This, where xi is in this range. This is very similar to this question we just solved. So it's the equality, so you don't have to deal with even adding x6. But remember this was xi bigger or equal to -3. Opposite to this, we have strictly less than 5 is the range now. So because of that, it's a slightly different question. You have to You have to do something different. Any ideas? Any?
Önce x1'e 0 koyup daha sonra x2, x3, x4 için
Hı hı. Any suggestions? Okay, let me start with some suggestions. Since you're looking for things that smaller range, we have to some way think about the ones that we don't want to count. The ones we don't want to count are the ones that xi is bigger or equal to 5. So bigger or equal to we can handle. We just handled bigger or equal to minus 3. So bigger or equal to 5 we can handle. That means if I count the ones I don't want, I can sort of take them out and find the ones that fits to this criteria. Okay? So think about things that you don't want to count. So the ones that say big set, you can say these are the ones that xi is bigger or equal to 0. Okay? So solutions with this, which we can count. We know how to count it. You can actually say that it will be the solutions with 15 choose 3. Okay? So the number, let's call this, say, set U. We know the number of elements in U is 15 choose 3. Because it's just no criteria, okay? So it's just the one that we just solved. Bigger or equal to 0. That means you will have 15 choose 3. Now the things we want to exclude are the ones that xi is bigger or equal to 5. Okay? But if you call this AI, solutions where xi is bigger or equal to 5, that means you have to exclude A1, you have to exclude A2, you have to exclude A3 and A4, which they all may intersect in certain ways. So you want to exclude these and count this set. Okay? So the answer will be this set. So how you count this set, where you excluding a union? So this is what we did on Friday, inclusion-exclusion principle. So what you want to calculate is this set, the union subtracted. Okay? And we have seen on Friday that when you have a union, the number of elements can be counted by some formula that involves the elements in the sets and elements in the intersection of two sets. So this will be the elements in U minus the elements of each of these. And then you add back the elements in the intersections. If there is anything, we don't know, but. And then you subtract the triples. And then add the fours. There's only one intersection of 4 things, so you just get this thing. And it could be even 0. I mean, you can look at these things and try to find each of these sets, number of elements. Then you have the formula for the answer. Now we found that U is this, and you can count the number of elements in each of these AIs very easily. Those are the solutions. So these are number of solutions, x1, x2, x3, x4 equals to 12, where one of them, say, let's choose one of them, say x1. x1 is bigger or equal to 5, but all the other ones are just bigger or equal to 0. So there's no restriction. So how many solutions like this you can find? We just did -3, so it's similar, right? So this is number of solutions with y1, y2, y3, y4 is equal to, you subtract 5. The -3 subtracted was +3, but here you just subtract 5. You just solve this with all the yi's bigger or equal to 0. So you can easily see that this is 10 choose 3. Okay? So each of these AIs are easy to calculate. They're 10 choose 3. You can also calculate the intersections. Say you calculate intersection of A1 and A2. This is the number of solutions to this equation with x1 bigger or equal to 5, x2 bigger or equal to 5, where x3, x4 are just bigger or equal to 0. No restrictions. Again, you take 5 out, another 5 out, so you get this number of solutions where these things hold. So you get 2 left. Each of these are positive. So how many solutions you have like this? 5 choose 3. So this is also 5 choose 3. You get 3, 5 choose 3. Now if you look at carefully, if you have all these things hold, that means 3 things will be bigger than 5. But they already have to be bigger than 15, some of them. And total cannot be 12 if you have some of the 3 is bigger than 15. So this is 0. There is nothing here. Also, this is 0. So you cannot have these intersections. They don't exist. They are 0. Which means I can now write my answer. Okay, just you need to put all these things in here to finish the proof. I will erase here so that you can see what the answer is. So the answer will be 15 choose 3 minus, they're all same, doesn't matter how you count it. So there are 4 of these things, and each of them is 10 choose 3. Let's 10 choose 3 here. And then the intersections, there are 4 choose 2 intersections, and each of them is 5 choose 3. And there's nothing else. So this is your answer for this question. Any question?
We can solve, I think, by defining new variable, for example, 4 minus xi equal to I1.
For minus?
y1, yi equals to 4 minus xi.
Yeah, but when you introduce minuses, then you have to put minus y into equation. So equation will have minuses in it.
No, actually, it will be much faster because I1, y1 plus y2 plus y4, y3 plus y4 will be equal to 4.
No. We introduce minuses, so you have to see that this was the equation, right? So this was the equation you wanted.
Yes.
And
So
you introduce minus.
16 minus 12 makes 4. So we will distribute that 4 to those 4 y's. It's 7 choose 3, I guess.
This is 4 minus y, not 4 plus y.
Yani -4 olarak olmuş.
You cannot avoid inclusion exclusion.
Like in this distribution, y will be between 0 and 4.
I mean, if you only had the upper bound, your idea will work. Everything will switch. But we also have lower bound. So the lower bound has to switch too. It will give you a new upper bound.
Lower bound will be satisfied because y will be at most 4 in this question, which is 4 minus 4 will always make it positive.
So you say that this will be one combinatorics formula? Like
Yes, 7 choose 3.
7 choose 3. So that's equal to that?
Calculate that.
Okay, so let's check. If it is correct, then I will listen to it more.
I calculate it and they are equal.
They're equal, okay. So how does it work? Let's look at it then, I guess. So we want to, let's see. So you introduce 4 minus x. So y has becomes because this is Fourier, excludes gives you no restriction. Yeah, I see that. Okay.
Condition of between 0 and 5 the solution
Yeah.
will work, but
Because this was small enough, yeah. Yeah. This, it's a correct answer, yes. But I can make it 65, and then this wouldn't work, right? So if this, instead of 12, it's for 65, then you're in trouble, right? It's just, so the suggestion was take yi equals 4 minus xi, right? So if you do that, you just switch the conditions. Now, instead of xi being 0 to 4, yi becomes 0 to 4. And then new equation becomes with 4 here. But because this 4 is small enough that this upper bound doesn't count. So it becomes regular bigger equal to 0. So it's, yeah, pure luck or chance. But that works, that is 7 choose 3. So, yeah. So this is an alternative answer. Okay. But in general, the numbers will be big. So if you switch it, you have some more conditions. So it's not going to work it without inclusion, exclusion. Okay, very good. In general, if you are trying to solve a problem which involves cases that you want to exclude, but if these cases are greeted in, like they are knitted in a certain way, that they may have intersections. Sometimes when you're trying to solve these problems where you need to exclude cases, it's often to make this mistake that you just take out all them separately. But if they have intersections like this, you have to take those cases out using inclusion-exclusion principle. You cannot just say that I would take them out like this. Because if they have intersection, you have to add them back and take out. So you have to use this formula this way. That's the warning. There's another question here that we can solve that involves stirring numbers. So this is the question. If n is an integer with n bigger or equal to 4, verify Any ideas, any suggestions? I want to remind you a couple of things about this, but recall that stirring numbers as mn is 1 over n factorial of these t's. This t's appears more in the combinatorics questions, which are the number of ways to distribute m distinct objects to n distinct boxes so that each box gets at least one object. So TMN is the one that comes up more straight in questions. But the stirring numbers is the one that also can come. As you see from n factorial, this is actually number of ways to distribute in n identical boxes. So we have distinct things and distributed to n identical boxes. So that. Okay. We developed a formula last time. If you remember, as Mn, we had a formula by inclusion-exclusion principle. Anybody remember the formula? It looked like this: n to the power m minus. Anybody remembers? N minus 1, n'in birisi, n minus 1 to the power m, n'in ikilisi, n minus 2. We drop by 1 and then it's the inclusion-exclusion principle, but you have to write it in a slightly different way. So here you get some meaningful thing at n minus 2, which ends with 1 to the m. And the last term is 0. So this is where the most meaningful thing. So if you look at this with n and n minus 2, you have to have n minus 2 terms on the left-hand side. Like you will be summing up n minus 2 terms. You have to go down from n minus 2 to the 1, which means that it will be a big mess. Okay? So the only way to verify this, not to use this formula. Okay? If you try to use this formula, it's not going to be verifiable. It will be a big mess. This is one of the miraculous things about stirring numbers. Many very ugly sums comes from stirring numbers turn out to be equal to something very simple. We actually wrote some of the other relations, but this is one of these questions that if you know the formula, you may not be able to show that it's equal to this. But you have to go back to the roots and try to see it in terms of this, and you have to write a proof. Prove this by a combinatorial argument. So this is something that I told you a couple of times, that you can prove something using a combinatorial argument. Means that you can say, I have this thing that I try to count. If I count it in one way, I should be getting this stirring number thing. And if I count it another way, I should be getting what is on the right-hand side. Okay? So we have to see basically how many ways you can distribute n distinct, like maybe to n minus 2 identical objects. N distinct objects to n minus 2 identical boxes. So if you can find a good way of explaining this, this is the left-hand side of this formula is this number. So number of distributions. And left-hand side, right-hand side is that thing. So you want to show that this is actually equal to the right-hand side. Which is this n choose 3 times n choose 4. So in some way you have to find a good way of counting this distribution which will result with this answer. So how many ways I can count, like distribute n distinct to n minus 2 identical boxes? Okay, because you have a sum, because of the sum rule, I have to have cases, right? So I have to have case 1 and case 2. These cases should be distinct. There should be no intersection. So if I can write 2 cases, and each case corresponds to these numbers, then I can say, okay, the sum is this. Okay? So if you distribute n things to n minus 2 identical boxes, what are the 2 cases that may happen? Yes, at least, yeah, this is the rule. At least one object with at least one. All in TMN these were distinct. In SMN these are identical. That's the only difference. So identical boxes means you don't care which order they are. That's the only difference. Think about this as you have n people, n of you, and we're going to group you in n minus 2 groups. So what will happen? What are the cases?
Önce şey yaparım, herkesi bir gruba koyarım, ondan sonra 2'yi dağıtırım.
If you first say I distribute these people, then it's a two-step process. We talked about this on Friday. It's a two-step process which remembers if one comes first, 2 later, or 2 comes first and then 1 later. Because of that two-step process here is not allowed. We do not want to record that information. So if you say first I choose these people, put them there, you do not get the right formula.
If each box contains at least one object, then there are already 2 objects then left. And then you have to think in the first case that 2 objects will be in one box.
So 3, 1, 1 combination.
Or there 2, 2 and 1, 1.
Yeah, these are only cases that are possible. It's either 3, 1, 1, 1, 1 or 2, 2, 1, 1, 1, 1. There's no other case. Very good. So this is first separation. That it cannot happen at the same time too, right? Either this way or this way. And suppose it's this way. If the boxes are not labeled, boxes are not important, how can you decide a distribution like this? What do you need to do to find a distribution like this? Choose 3 people who will be in the same place, in the same box. As long as they know they will be in the same box, if the boxes are not labeled, that's exactly this distribution. Choose 3 people who will be in the same box. That's why it's then choose 3. Think of this like you are n students and the school says we only have n minus 2 rooms. You don't know which rooms you are going to get in the dormitory, but they say that all the rooms are single except one room is 3. And then how can you distribute? You will find volunteers or 3 students who are willing to be in that room. And the rest is not important. The rooms are not marked. Okay? So this is and choose 3. Let's look at this one. How can you find this one?
2 choose 4.
2 choose 4.
And then 4 kişi yani kişiden seçeceğim. Ondan sonra o 4'ü 2.
You can do this in 2 steps. First, choose the 4 people who will be unfortunate, who will not have a single room. Choose those 4 people. Now, out of 4 people, you want to choose 2 to separate them. But how many different ways you can separate 2 people? You can choose the 2 out of them. But this choosing 2 will say these 2 first and the other 2. You have to divide by 2 so that it's not important which 2 first chosen. And this number is 3. That's why the answer is this. As you see, I mean, except the fact that this is stirring numbers, all of this is usual combinatorics that we have been doing this all analysis of its addition rule, product rule, cases, multiplying. So it's all the basic combinatorics, but you have to put them together so that it's all correct. So this is the answer to this question. I think we probably have time. Okay, 2 minutes. Two things I should say. There are 2 minutes left, so we will be finishing. If you want to take your quiz, this is all the quizzes I have from graded quizzes. You can take them. Other thing is that I suggest that you solve problem 2, for example. This is a nice question in the sample. Solve the negative power rules. Try to solve at least one combinatorial argument question. Solve at least one combinatorial argument question. Also print this and come to the class with a printed one. I'm just joking. But if you had it solved before, you could have asked me more direct questions from this set. But this set is supposed to help you. The number 12, for example, is Thomas, Stuart, Craig, chores. That's a storing number question. So you can face a question that has wording in it, but and then the answer is T83 or something. So the answer becomes like one of these numbers. So the question is just word problem, but then the answer is this. So you should know that which word problems corresponds to storing number questions. And if you get stuck with them, come Thursday at 1:30, I can answer questions. Okay? Good luck in exam Friday.